Hello everyone, welcome to lecture 2 of classical mechanics, Physics-411. This is part 1 of lecture 2. Let's start with the review of what we did last time. Last time, we considered various conservation laws for a single particle of mass m moving at a velocity v under the action of force F, and the particle m itself was located at radius r. We derived the following conservation laws. Momentum conservation law, angular momentum conservation law, and the energy conservation law. And we wrapped up the lecture with generalizing this concept to systems of interacting particles. So many particles interacting with each other and being tugged by external forces. We have derived the momentum conservation law for such a system of interacting particles. So we can represent a system of interacting particles like that. So there is a bunch of particles there. Let's recall what exactly did we do in order to derive the momentum conservation law for that. We wrote down equations of motion for each of the particles. We added them all up and figured out how this collection of particles behaves as a whole. And what we found out is that a system of interacting particles behaves the same way as a single point particle located at the center of mass of this system moving at velocity of the center of mass and being tugged by the sum of all the external forces. And having mass m, which is the sum of all the masses of individual particles. From here, we can make the conclusion that if the sum of all the external forces vanishes, then the total momentum of the particle will actually be conserved. Which is a really great result because we don't have to consider the internal dynamics of the particles in this interacting system. All we care about is how its center of mass moves around, and that's described in a very simple way by the dynamics of a single point particle. Okay, let's get started with the second part of our lecture number 2. All right, now that the board is clean, we can get started with our second part of lecture 2. What are we going to be talking today? We're going to be continuing the discussion of conservation laws for a system of interacting particles. Namely, we're going to start with conservation of angular momentum for many particles And then we will finish off with the discussion of constraints and the Lagrangian approach. You can read up more on this in Goldstein chapters 1.2, 1.4, and 1.6. And as usual, if you have any questions, you can always ask them during the office hours. So let's get to it. Conservation of angular momentum. How are we going to go about this? Well, it's pretty similar to what we've done before for linear momentum, but there is a twist. So let's draw a diagram. So suppose that we have a sun, and we have the Earth that's on an orbit around the sun, so it has an orbital velocity. But in addition to simply orbiting around the sun, the Earth also has own spin, its own degree of rotation, v rotation. And this internal spin is what makes the conservation law of angular momentum for systems of particles more complicated than for linear momentum. Let's take a look at how it works. So let's write down the equations of motion for the change of angular momentum with time. So for a single particle, that would be dLi dt is equal to the mass of the particle times the position of the particle cross the velocity of the particle. So this is just the angular momentum of the particle. And then we take the time derivative of this. That will be equal to the torque that's acting on this particle. As before, what are we going to do? We're going to sum up these equations for these equations of motion for a single particle. We'll sum them up together to get them for many particles. So here we're going to get dl total dt on the left-hand side. And here we're going to get the summation of mi ri cross vi. And on the right-hand side, we're going to get the total torque. And this just adds up to the sum of all the external forces, with the internal torques going away. This is because internal torques cancel out just like the internal forces canceled out when we derived the conservation law of linear momentum. And this is because of the assumption of the strong law of action equals to reaction. So now that we've gotten this, it's really appealing to say that this angular momentum, L total, is equal, but in fact it won't be, simply RCM times VCM times the total mass. It turns out that is not true. And that is because of the presence of the extra angular momentum associated with the spin. So let us take a look at it. How does that work? Well, let's take L total and write it out. For that, we're going to need a diagram. So this is our system of interacting particles. That is our center of mass, and we're going to break down every radius vector Ri into the sum of RCM and R prime, which is the difference between the vector Ri and RCM. So here, Ri is equal to RCM plus R prime. So here, if we were to take that and plug that into here, and also into here, because this implies also that Vi will be equal to VCM plus V prime. So if we plug both of these into this expression, we are going to get the sum over I of Mi times RCM plus R prime, that's for the radius, crossed into VCM plus Vi prime for the velocity. And then we can continue over here. So first of all, let us break this down into different terms. So one term here will be Mi RCM cross Vi prime. The other term will be Mi Ri prime cross VCM. And then there will also be two other terms, Mi times Mi times RCM cross VCM. This is the term that we expected to have, but there is going to be an additional term, which will be the sum of Mi Ri prime cross Vi prime. So what is the physical meaning of all these four terms? Well, first of all, let's figure out which ones of these terms are actually going to drop out. Well, here, for instance, we can take RCM out as a factor, and we're going to be left with the sum over I of Mi times Vi prime. But the sum of Mi times Vi prime from here will actually be 0 because of the definition of the center of mass. So this term is going to go away. This term, here we can separate the sum out by taking out the velocity of the center of mass. And here we're going to get also 0 because by definition of the center of mass, this sum also vanishes. So it means that we are left with just these two terms. The meaning of this term is very clear. That's angular momentum associated with orbital motion. So this is associated with the motion of the Earth as a point particle around the Sun. This term, however, is associated with the internal spin of the Earth. And it is this new component that we really have to be careful and mindful about in order to make sure that we correctly compute the angular momentum of the system. From here, the conclusion that we can make, though, is the following, that, and from here as well, that if the total sum of the external torques is 0, then the total angular momentum of the system is going to be conserved. And with that, we're going to be ready to move to the next section, 3 of our lecture 2. Please do not forget to fill out the quiz, and I'm going to see you in the next part. Hi, hello everyone. Welcome to part 3 of lecture 2. And we're going to start the new exciting topic of Lagrangians. So why should we even bother about Lagrangians? I mean, we know everything comes out of F equals 2ma anyway. What's the point of, inventing anything new? Why would I want to do that? I'm already happy with what I have. Well, that's because Lagrangians offer a powerful, I would say, extremely powerful way of getting equations of motion nearly automatically. That is really something. So if you haven't had a chance to play around with Lagrangian approach, now you're gonna have a chance to do that. Let me give you an example first of what sort of new elements we're going to have to learn in order to use Lagrangian approach. And one of these new elements is the concept of constraints. We are dealing with constraints every day, and mechanical systems do too. So here is an example of a system with constraints, which is a simple pendulum. Here, the particle of mass m cannot move anywhere at once. It can only move along a surface of a sphere of radius d, centered at the point of attachment. So the distance of mass is constant from the point of attachment. So this is an example of a constraint. And how would we go about solving for equations of motion, finding equations of motion in this case? Well, we would introduce the force of gravity, introduce the force of tension, balance them out, and obtain the equations of motion in this way. But this is old way. So let's take a look at an example number 2 of a solid body. So this one was a pendulum. This one is solid body. So solid body, you can represent it like this. So there is a bunch of points, all of which are rigidly attached to each other. So if you pull on one, you pull the entire body with it. So clearly there are a lot of constraints that specify that the points don't move relative to each other. So there is a huge number of constraints. Another point is that if we were to write down equations of motion for each of the pieces into which we break the solid body and then introduce all the forces of constraint, it's going to be impossible to solve this. Almost impossible. using a conventional approach. So here, the fact that we had to rely on tension means that we had to include forces of constraint. Is there a way for us to try and avoid including forces of constraint, which will significantly simplify solving for the dynamics of such complicated systems? And let's try and just get a count of how the constraints affect the degrees of freedom. So suppose that we have two particles R1 and R2 that are evolving in time, and we can generalize this to n particles. For every particle will have 3 degrees of freedom. Every particle can move up, down, left, right, and back and forth, right? So n particles means that there is 3n degrees of freedom, which also means that there are 3n equations of motion, one equation of motion per degree of freedom. So this is where we can start introducing a constraint. How does constraint look like? Constraint is a restriction on where the different particles of our system can be. So we can write it down formally as a function of f of the positions of all the capital N particles in our system and perhaps the time. So that is an example of what is usually called holonomic constraint. If the constraint doesn't have the time dependence, then it would be scleronomic. And if the constraint explicitly depends on time, then it is rheonomic. So if the constraint doesn't depend on time explicitly, it's called scleronomic constraint, but if it has an explicit dependence on time, then it's called a rheonomic constraint. And the most important takeaway point about constraints of today is that every constraint reduces the number of degrees of freedom by 1. And that is really important. Particularly for the next part of our lecture, where we're going to be trying to figure out how many degrees of freedom we have left after the constraints have been applied. I'm going to see you soon. Hello and welcome back to our lecture number 2, part 4. Now we're going to talk about the importance and physics of constraints. Over here we have shown that an application of one constraint reduces the number of degrees of freedom by 1. So let's try and apply this rule to the 2 examples that we considered before to figure out how many degrees of freedom they have left after the constraints have been applied. So in the case of a pendulum, we have a particle of mass m that is free to move as so long as its distance from the point of attachment is fixed to be constant, d. So without this constraint, if the particle is free, we would have, let's consider a one-dimensional pendulum, so it can only move in the plane of this light board. Number of degrees of freedom before the application of constraint would be two, because the particle can go anywhere it wants, up and down, left and right, within the light board. But after the application of the constraint, the number of degrees of freedom will go down by 1, because every constraint reduces the number of degrees of freedom by 1. So what about the solid body? So here, number of degrees of freedom for a solid body made up of, n particles. So let's consider, for instance, 4 particles. So 4 particles, each particle has 3 degrees of freedom. It can move however it wants. And there are 4, so there will be 3 times 4 degrees of freedom. So for n particles, we will have 3n degrees of freedom, and after the constraint, it turns out we will just have 6 degrees of freedom left. How can we understand that? Well, the 6 degrees of freedom will come from 3 degrees of freedom that correspond to the translational degrees of freedom, and 3 that correspond to rotational degrees of freedom. But when you look at this, it's not really clear why a system of 4 particles would lose magically the right number of degrees of freedom to give you 6, or let's say it's 40 particles. Let's think about it. Let's think about it a little bit. So I chose 4 particles because what I can do is I can build a pyramid on top of these particles. And so we can immediately see that each edge of the pyramid will give us 1 constraint. So we have 4 particles, 12 degrees of freedom, but then we also have 1, 2, 3, 4, 5, 6 constraints. So 12 minus 6 will give us 6 degrees of freedom after the constraints have been applied. So suppose we want to now build up our solid body by adding more particles. So because it's a solid body, every new particle that we add, in order for it to be solid, not moving around, we need to connect it to at least 3 points in the solid body. Because if we connect it to 2 points, it can swing. 1 point, it can do various things. 2 points, it can swing. And 3 points, we're now going to have it rigidly attached so that it can't move without the rigid body. So if we attach 1 more particle, then the new particle will bring 3 new degrees of freedom, but it will also acquire 3 new constraints, so that the number of degrees of freedom after the constraints have been accounted for is 0 that every new particle brings in. So you can keep adding particles like that, and yet these particles will not give us any new degrees of freedom. So that's really important to know, that In fact, solving for rigid body dynamics is actually not that hard because we only have to deal with 6 degrees of freedom. That is provided we don't have to worry about the forces of constraint, which is what the Lagrangian approach promises us. So that's why it is super cool to use it. So what actually do we want out of Lagrangian approach? What we want is we want equations of motion for the remaining degrees of freedom after constraints. So we want equations of motion for the remaining 6 degrees of freedom in the case of solid body, or for the remaining 1 degree of freedom in the case of a pendulum. So how would we go about doing that? Well, we will introduce generalized coordinates q1, q2, qn. And here, n is the number of degrees of freedom after constraints. So what does it mean that these are generalized coordinates? It means that we can describe the full state of the system if we know these coordinates. So what that means is that we can write down the position of particle number 1 as a function of the generalized coordinates and time. And we can do that for every particle. So this is where we're going to leave it today. And all I wanted to tell you now is what we're going to be doing next time. And next time, we're going to introduce, we're going to see how to use the generalized coordinates. We're going to introduce the principle of virtual work. And finally, we're going to derive Lagrange's equations. Thank you so much for your attention. This was a lot of fun for me. I hope it was a lot of fun for you. Don't forget to fill out the quiz, and I'm going to see you next week and during the office hours. Thank you.